To continue our discussion on the electrical phenomena in insulating materials, we will introduce a new variety of dielectrics, new classes of dielectric material called ferroelectric, piezoelectric and pyroelectric ceramics. Well, they are also dielectric materials, they have the dielectric polarization. The primary difference is they do get polarized even in the absence of electric field. So, they have a spontaneous polarization which does not need any electrical field, external electrical field to get them polarized. Of course, under normal conditions you do not find the polarization as such, they are all in the atomistic level. So, on a larger volume, in a bulk material, there is as such no polarization until unless we do some special treatment to them. The group are called ferroelectric, piezoelectric and pyroelectric ceramics. They have certain common features. So, we will be discussing them together, but to start with we will have a discussion on ferroelectric and then go to the piezoelectric as well as pyroelectric ceramics. So, our discussion first starts with the ferroelectric ceramics. When you talk about ceramics, they are primarily perovskite kind of compounds. However, besides ceramics there are many other ferroelectric ceramics which are known. In fact, ferroelectric materials in general are characterized by the presence of spontaneous dielectric polarization as I have just mentioned. So, even without the electric field they have their own polarization. These polarization are existing because of the dipoles, they have a pre-existing dipoles in these materials even in the absence of external electric field, that is the basic meaning. They originate from the minor deviation from the crystallographic symmetry. So, basically it is the crystallography which is known to be the origin of this kind of behavior. Of course, that leads to many other thermodynamic as well as different kind of phonons and phonon modes and so on. We will not be discussing all those here, but primarily considering the crystallographic origin of this property. Either there are deviations in the crystallographic symmetry or there are some inherent asymmetry in the crystal structure itself. So, both of them can lead to spontaneous polarization or dipole moment generated. The materials are electric analog of ferromagnetic materials. In fact, as the name suggests, ferroelectric materials, they are in fact developed much later than the so called ferromagnetic materials, and because of their similarity in many ways they have been named as ferroelectric rather than ferromagnetic materials. If you go to the history of this, it was not the perovskite family of compounds which were discovered first, but it was discovered in around 1920s in a soluble salt called Russell salt, which is nothing but sodium potassium tartrate. The formula is also given there. Later on, about a decade later, one more compound was also discovered having the similar properties, that is shortly an in short name as KDP, the potassium dihydrogen phosphate. It is also a soluble salt. Those days these are the materials of which single crystals could be grown relatively easily. So, because that is the reason they have been studied in the single crystal form, and the properties were basically discovered when the single crystal properties were investigated. In those days it was very difficult to grow single crystal of ceramic materials because of their high melting point, and therefore, these are the materials which were used or could be produced in a single crystal form, and their properties was discovered in those materials. Later in 1940s, the ferroelectric ceramics was first discovered in barium titanate. Barium titanate is a perovskite family of compound. We have discussed its structure earlier. So, it is basically a mixed oxide of barium oxide and titanium dioxide, and its melting point is much above 1000 degrees centigrade. So, it was difficult to make a single crystal of those, but it could be developed around 1940s, and that was the beginning of a whole group of ferroelectric ceramics which has been discovered later on. So, since then hundreds of compounds have been identified having the ferroelectric property. Not all of them are ceramics, as you can see from this display, but many of them are ceramics, and barium titanate is one of the most important materials which has been used for practical applications or industrial applications. What is the structure of barium titanate? As it has been mentioned, it is basically a perovskite structure, and perovskite, as you have discussed earlier, it is a family of compounds, and although the particular name relates to calcium titanate, the mineral calcium titanate, but the structure, it is a structure type, and a large number of compounds do crystallize in this particular form, and that is all of them are called perovskite compounds. So, barium titanate is an important member of this group, and as per the description, this is a very simple description of barium titanate structure. There are titanium is octahedrally coordinated with oxygen. So, the open circles are actually oxygen sitting in a cube faces. So, all the 6 faces, center of the cube faces are occupied by oxygen. Titanium is a center of the cube, and the corners are occupied by barium. So, barium and oxygen together form a closed packed cubic structure, and titanium occupies only a part of the tetrahedral sites. So, that is the basic description of barium titanate perovskite structure. If you look at some of the characteristics of barium titanate structure, as had been mentioned, barium titanate is the most important member of the perovskite family of the ferroelectrics. Okay. So, whenever you talk about ferroelectric ceramics, we do talk about barium titanate, and that becomes a representative compound to discuss all the different properties of ferroelectric ceramics. It possesses 4 different polymorphs with different crystal structures. Although whenever talk with barium titanate, we do talk about perovskite structure, and anybody asking what is the structure of barium titanate, the answer is perovskite, but it is really not true. It is really not true. It is only one of the polymorphic forms which has a perovskite structure. Others do not have a perovskite structure. They have a different structure, different symmetry, and in fact we will discuss them later on in this class. Cubic perovskite, as just mentioned, is the only one of them. Okay. So, it is only one out of 4 structures where barium titanate possesses. The origin of the spontaneous polarization, as has been mentioned, spontaneous polarization or even in the zero field arises basically from the distortion of the crystallographic structure or the crystallographic lattice or the atomic positions in the crystal structure. So, this is what kind of distortion, although we describe it as a cubic symmetry, but it really does not have a cubic symmetry. There is little bit of distortion in the c direction, and there is a displacement of the positive charges, center of the positive charge and the center of the negative charge, even without the application of electric field. So, even in the absence of electric field, the structure has a some amount of distortion. If we take the cross section of this cube, these are the oxygen ions, okay, these are the oxygen ions, these are on the two side surfaces, this is on the top surface, this is on the bottom surface, and this is on the front surface. So, there are 5 oxygen ions you can see here from the cross section, and all these oxygen ions are displaced little bit downwards, and the distance which is supposed to be on the center of this face, it is not exactly on the center of the face, it is about the distance is about 0.13 angstroms below. So, all of them actually have displaced from their symmetric position. They were supposed to be on this line, but they are displaced by about 0.1 angstroms. So, there is some amount of displacement, distortion from the symmetric structure, and because of that, the black one is titanium, the positively charged ions, and also the barium ions are the positive ions which are at the center. So, with respect to the center, of the positive, all the positive charges, the oxygen ions are displaced downwards, and that is how you create a dipole, where the positive charges are upwards and the negative charges are displaced little bit downwards. So, the center of the positive charge and the center of the negative charge is displaced, is not exactly coinciding with each other. So, there is a distance of separation of d, and therefore, you have a dipole moment. So, dipole moment is generated just like that because of the distortion. So, these are the lattice parameters, as you can also see here, A and B, these are A and B parameters. So, A parameter as well as B parameter is exactly same 3.98, whereas the C parameter, the vertical axis is slightly more, the vertical dimension unit cell is slightly more, 4.03. So, that is the origin of the spontaneous polarization, and although we talk about perovskite structure, but in fact the perovskite structure do not have the dielectric polarization or the spontaneous polarization. It is the distorted form of the perovskite or having a tetragonal symmetry, because A and B are equal and C is different. So, it is a tetragonal symmetry which gives rise to the spontaneous polarization. So, one has to carefully remember that perovskite structure really does not have the spontaneous polarization. In fact, it is not a ferroelectric phase, actually it is the distorted perovskite or the with some kind of tetragonal distortion that actually gives or produces the spontaneous polarization. So, as a result of one's spontaneous polarization, what are the things one can expect? Since we have a spontaneous polarization, a permanent dipole moment are already there because of the lattice distortion. Out of the 4 different mechanisms of polarization, it is the orientation polarization dominates here. So, that was mentioned in an earlier class that ferroelectric ceramics are dominated by this kind of orientation polarization mechanism, which is the basic mechanisms giving to the dielectric polarization. So, that is one consequence of the spontaneous polarization. There are ferroelectric domains within which all the dipoles are in parallel orientation. So, since there are permanent dipole moments, dipoles are already there. So, these dipoles in fact not individually, they are oriented in a random fashion, no doubt, but individually they are not oriented in a random fashion. There are some clusters. So, in those clusters they have a parallel orientation. So, individual maybe unit cells or the individual dipoles, they are not completely random, but they have certain amount of ordering within certain area, and these are called domains. So, within that domains the dipoles are parallelly oriented, and therefore, they have a net polarization. However, there are some large number of such domains adjoining each other, just like crystal structure, just like grain boundaries or grains in a polycrystalline material. So, you have also a domains, a large number of domains forms the whole volume of the crystal or the material. So, these domains do have a net polarization or net dipole moment, but they are randomly oriented. So, individual dipoles are not randomly oriented always, they have a groups. So, as a group they form a parallel orientation, but between the groups they have random orientation. So, we will always have in any ferroelectric material we will have a domain structure, just like in a magnetic ferromagnetic domains in a ferromagnetic materials. So, we have domains and we will schematically show what exactly the domain look like. At 0 field there is no net polarization, because I just indicated these domains are oriented randomly, not the individual dipole moments or dipoles, but as a group they are oriented randomly with each other. So, because of that there is no net polarization at 0 field. These we have earlier discussed about the linear dielectrics, where polarization is proportional or directly proportional to the electric field. But in this material, the ferroelectric material are the examples of nonlinear dielectrics, giving rise to ferroelectric hysteresis when polarization is plotted against electric field. So, they are a nonlinear curve, it produces a nonlinear curve when polarization is plotted against electric field, unlike the linear dielectrics which are non-ferroelectric dielectrics. Okay. All dielectrics are not certainly ferroelectric, but ferroelectrics forms a specific group of dielectrics. On application of the field, favorably oriented domains grow at the expense of the not so favorably oriented domains. When you apply an electric field, there is a change of orientation, and all the dipoles tend to orient themselves along the application along the direction of the field. However, all of them do not do it in a random manner. There is a process by which this orientation changes from a completely random orientation to a preferred orientation, and this is by change of the domain pattern or the domain size. So, to start with, there will be some of the domains will be favorably oriented with the application of the direction of the electric field, whereas others will be completely misaligned. So, when you apply the electric field, favorably oriented domains try to grow, size of them try to grow, and the unfavorably oriented wants to shrink. So, that is how ultimately at the end of the process all the domains will have a parallel orientation aligned with the direction of the electric field. So, at the end all of them will align parallelly and you have a maximum polarization possible at that stage. So, that is what we call a saturation polarization. So, beyond that it cannot change. We will see how it develops. The polarization become maximum, that is what we just mentioned. The saturation, that is what called the saturation polarization, when all the domains becomes parallel to the direction of the applied field. So, this is also another consequence of having a spontaneous polarization and a domain structure. Well, this is what we mean by a linear dielectrics and non-linear dielectrics. On the left you have a linear dielectrics that the relationship is shown in one of the earlier classes, and the slope is proportional to the dielectric constant. And here is on the right we have the non-linear dielectrics which arises or which we see in case of ferroelectric materials. So, when we apply electric field at 0 field, of course polarization is 0, although there is spontaneous polarization, but the overall polarization is 0, and as we increase the electric field the polarization increases, but not in a linear fashion. It follows a curvature here, a kind of concave curvature, and then becomes a convex curvature. So, ultimately it becomes a saturated at this some level. Now, here are the domain structures, which have been shown here. This is a domain structure, these are individual dipoles, the arrows indicate here is the individual dipoles, okay. Whereas you can see some kind of a line here, these are the what we call the domain boundary. So, this is one domain, one can see all the dipoles are oriented in a particular direction, upwards in this case, whereas in the next domain they are oriented downwards. On the other side, this is also another domain where the dipoles are oriented horizontally towards the left, this is towards the right, and this is again towards down and then left and right. So, these are about 4, 5, 6 different domains available, and in all the domains of course they have a parallel orientation, whereas with the neighboring domains they may have anti-parallel or a 90 degree orientation or a 180 degree orientation. So, accordingly, in fact, just like in magnetic materials we have a 90 degree domain or domain boundary or a 180 degree domain boundary and so on. So, at 0 field of course the orientation is such the net dipole moment is 0 and you do not have a polarization. So, polarization is 0. Whereas, if you apply electric field slowly the domains try to grow. This is the direction of the electric field here upwards. So, whichever domain has a upward orientation like this middle domain will try to grow, and that is what has happened here. You can see the middle domain has grown and the side domains has disappeared. So, there are of course still some side domains left here, not all of them has been disappearing, but slowly it is getting disappearing as the electric field is increased. So, somewhere around this is the situation where most of them are oriented upwards, but still few domains will be left to be converted. And when you come to this level, as you can see all the domains, all the dipoles are oriented in a particular direction, and that is along the direction of the applied field. So, this is where no more change can take place, and there is basically one can say a single domain system. So, all the domains, either a single domain or multiple domain may also be there, but their domain, their orientation of the polarization will be all in the along the applied field direction. So, this is where we get a complete transformation from a random state to a complete ordered state. Okay. So, random orientation to a completely ordered state, and even after the application of further field, there will be no further change in polarization, it will almost saturate here, and that is the value of what we call the saturation polarization. So, this is the relationship of a nonlinear dielectrics or a ferroelectric dielectric compared to a linear dielectrics, which is non-ferroelectric dielectric. Okay. So, that is the basic difference. So, that gives rise that leads us to a discussion what happens when we actually cycle the electric field. That means, we increase the electric field in this direction and then comes back in the negative, comes to 0 and then goes to the negative direction. So, what happens to that? What happens to the domain structure? And this is what exactly happens when if you cycle the electric field. And this we have discussed, this is your saturation polarization. We have all the domains oriented in a particular direction, again in the application of electric field, direction of the electric field. However, after the saturation, if you try to lower down the applied voltage, then it does not follow, this particular path, it is not a reversible in that manner. Okay. It does not exactly follow the same curve which would have been plotted. In fact, it starts from 0 here, it goes to, this follows this dotted line, comes to this, and then when we reduce the electric field, it follows a separate different curve, and it comes to this. Even at 0 field, there is a polarization, a positive polarization remains there even at the 0 field. Although we have started with a 0 polarization, but we have ended up with a positive polarization even at 0 field. So, this is what we call the remnant polarization here, the remnant polarization, because this, the reason is it is the way we change the electric field and the time it takes to change the orientation, because it is basically orientation polarization. So, the atoms have to move from one place to the other. So, it is a sluggish process, it is certainly a very sluggish process, and therefore, even if you reduce the electric field, the atoms has not come back to its original position. Okay. So, as a result of that, there is a phase lag. There is a phase lag between the applied electric field and the movement of the domains or the change of orientation of the domains. So, we have remnant polarization, and if you want to make it 0, that means polarization, to bring it 0, you have to apply a negative bias or negative field. So, that negative field EC is called the coercive field. So, the negative bias or the negative field what is needed to bring back the polarization to 0 is called the coercive field. And then of course, if you want to go to the negative direction further, then it will saturate once again in the negative direction. So, you can see here, this is one kind of a situation, saturation, all the domains are parallel and in the direction of the applied field, but on this side here it is reverse, because the applied field had changed, direction of the applied field had changed. So, also the direction of the individual dipoles. So, in between of course, you have still a domain structure like this. This is a structure which is very similar, which was there at this point. So, this also is a 0 polarization, this is also a 0 polarization. So, they have more or less the same domain structure which you have seen earlier at this point. So, this is very similar, but here it is more or less what you saw, what we can show here. So, this is how the domains actually change, and as a result of the domain movement you get a hysteresis, what we call a hysteresis curve. By increasing the applied field, it follows one particular variation, one particular curve, whereas by decreasing it follows another. So, it goes on, if you cycle it follows like that. So, initially it started with this, and once it reaches a saturation it continues in this pattern. So, this is what we call the hysteresis loop, sometimes called hysteresis loop or in hysteresis diagram. So, all ferroelectric material, this is one of the characteristics, and that is because it has a domain structure, and the domain structure or the movement of the domains or the orientation of the domains takes a larger time than the application of the electric field. So, this is our ferroelectric hysteresis. Then we come to another characteristics of all ferroelectric material, that is the temperature dependence of the polarization. Temperature dependence of polarization, of course, is basically the mechanism is orientation polarization. So, it has that particular characteristics. We have seen this equations earlier. The polarization is equal to epsilon naught k prime minus 1 E is the electric field, and that is also equal to, in terms of the polarizability, in terms the alpha is the polarizability, number of dipole moments per unit volume, the polarizability, the polarization of each one of them, and multiplied by E prime. E prime, as we introduce, it is a local field, not the external field, but the local field experienced by the by individual dipoles within the solid. Okay. So, because there are other dipole moments or the other dipoles which have also certain influence on its neighboring dipoles, as a result the effective electric field is different than what we apply from outside. And one can calculate that there is a relationship between the applied electric field from outside and also the polarization of that particular volume of material. Okay. So, E prime can be related by this equation, which has not been derived here, but one can accept that E prime equal to P E prime equal to E plus P by 3 epsilon naught. So, this is the expression of E prime. If we continue, so the polarization and the dielectric receptivity may also be expressed. These are as per definition from the earlier relationship. Polarization then in terms of the applied field n alpha E by 1 minus n alpha by 3 epsilon naught. This is the expression of polarization, and this is the expression of susceptibility, dielectric susceptibility chi, which is again k prime minus 1. This has already been introduced, and then this also in terms of because this is the P. Okay. So, if you just replace P here, you will find that. Both these terms approach infinity. Now, both these terms have this value this term n alpha over 3 epsilon naught. If somehow this becomes 1, this becomes 1, this becomes infinity, polarization becomes infinity, and the susceptibility also becomes infinity, provided this term becomes 1. Okay. Now, under certain situation this terms really becomes 1, and that is what we will see under what conditions this term can be 1. It is also known that the orientation polarizability alpha is inversely proportional to the absolute temperature. Okay. So, this is the actually the temperature dependence of the overall polarization comes from this particular equation, that is the relationship alpha O, it is not alpha 0, it is alpha O, the orientation polarization is actually inversely proportional to the absolute temperature through this relationship. C is a constant, some kind of a constant term, and K is a Boltzmann constant. So, it is actually inversely proportional to temperature. Okay. So, this is one relationship of the polarizability, orientation polarizability. As the orientation polarization predominates in ferroelectric material, one may imagine a critical temperature will be reached when n alpha by 3 epsilon reaches the value of infinity. So, this if this alpha, in fact this alpha is basically alpha 0. So, once it reaches unity, then at a particular temperature, so that temperature becomes quite an important parameter for us. Thus, at T equal to T c, it may be written this, if this satisfies, then so T becomes T c when this n alpha by 3 is n alpha naught, actually not n alpha O, and 3 epsilon naught becomes 1. So, this is a situation where the temperature we consider as a critical temperature, so which provides an expression of the critical temperature as T c equal to this value. Okay. So, n alpha, just by transposing it one can find out this is the expression for T c. And therefore, one can write the chi, the susceptibility, the dielectric constant, and the polarization. These are related to each other and then also related to this expression 3 T c by T minus T c. Okay. This is a critical temperature and T is actually the real temperature at any variable temperature, and T c is the particular characteristics temperature of the ferroelectric material. This relationship is known as Curie-Weiss law, and T c is known as the Curie temperature. So, this is one of the another very important characteristics of ferroelectric material. All ferroelectric material has a follows Curie-Weiss law and also has a critical temperature known as the Curie temperature. As T approaches T c, actually it is not T, it is not T 0, it is actually T c, chi K prime, the dielectric constant as well as polarization tend to reach infinity. So, this is a very important characteristics which arises from the Curie-Weiss law, and all ferroelectric material follows this particular law. So, consequently all ferroelectric material actually goes through the dielectric constant or the chi or the polarization goes through a very high peak at a particular temperature called T c. And this is the characteristics. So, you have a relative dielectric constant here on this side and temperature on this side. So, at a particular temperature which is known as the Curie temperature, the dielectric constant goes through a very high peak. In fact, as has been mentioned, it goes through it, ideally it should be infinity, but actually in practice it goes through a very steep or a sharp peak. Okay. So, this is the characteristics of the ferroelectric behavior as a function of temperature. With this we come to the different polymorphic forms of barium titanate, as had been mentioned earlier. Perovskite or cubic perovskite is only one particular structure of barium titanate, it has 3 different other structures at different temperature ranges. So, these are like this, sorry. These are 4 different polymorphic forms. Here is cubic. In fact, cubic is the highest temperature polymorph, and it is stable above 120 degrees centigrade. Okay. Above 120 degrees centigrade, this is the cubic perovskite is the stable polymorph, and because of its symmetry, because of its absolute symmetric structure, the spontaneous polarization is 0. Okay. So, there is no spontaneous polarization or dipole moment is 0 because it does not have a dipole, okay, because of the symmetry. Whereas, the kind of deformation, the kind of deviation from symmetry we have discussed earlier, which gives rise to a spontaneous polarization, is actually occur in tetragonal form. So, instead of a cubic have been shown everywhere in all these pictures, that is the basic cubic structure, and which has been either pulled along the face diagonal or it has been pulled along the body diagonal. Here it has been pulled along the C axis. So, this is the direction of the polarization, okay, that which I have seen earlier. The dipole moment is along the vertical direction of the unit cell. So, there is a tetragonal distortion here, and the PS is along the 001 axis. This is the 001 direction. From the points of view of the crystallography, one can define this C axis is actually the direction of 001 axis, a 001 direction, and this tetragonal polymorph is stable within this temperature range between 5 degrees centigrade to 120 degrees centigrade. Okay. So, it is very close to 0. So, almost slightly below room temperature to slightly above room temperature. That is the range where tetragonal symmetry is stable, and you have a spontaneous polarization here. If you go still lower temperatures, then it has a different distortion. This was pulled along the C axis, this has been pulled along 110 axis, that is the face diagonal. Okay. If you pull along the face diagonal, this results. Okay. So, you have a orthorhombic structure, and the polarization direction, crystallographic direction for the polarization, permanent spontaneous polarization is actually 110, and this is stable between -90 to +5 degrees centigrade. So, this is what happens in a lower temperature. If you go still lower temperature below -90, then there is another form which is more stable, and that is the symmetry becomes rhombohedral. So, from cubic to tetragonal to orthorhombic and rhombohedral as you go down the temperature range, and in this case it has been pulled along 111, which is basically the body diagonal. One is the face diagonal, 110 is along the face diagonal, here it has been pulled along the face diagonal, and that is how the distortion comes here, and if you pull along the body diagonal, then the rhombohedral structure comes. Okay. So, the spontaneous polarization is along 111 direction, and this is stable below 90 degrees centigrade, -90 degrees centigrade. So, this is the 4 different polymorphs, and all these are ferroelectric. All these 3 structures are ferroelectric structures, whereas this is not non-ferroelectric. In fact, this is a simple what we call paraelectric, as in case of magnetic materials you have ferromagnetic above the Curie temperature transforms to a paramagnetic material. Here also the same thing happens, and it is termed as paraelectric material. So, it is actually this perovskite structure is actually a linear dielectrics. So, while these three structures are nonlinear dielectrics, this structure is actually linear dielectrics. Well, since there are different forms of polymorphs and some of them are paraelectrics, some of them are ferroelectric and one of them is paraelectric. If you try to plot the dielectric constant as a function of temperature over a wide range from -200 to 120 degrees, 120 degree incidentally is the Curie temperature of barium titanate. So, above that there is a, or at that temperature there is a very sharp peak and then it drops and it follows the so called linear dielectrics behavior. In below 120 these are all ferroelectric forms and each phase transformation, wherever there is a phase transformation, this is from tetragonal to orthorhombic and then orthorhombic to rhombohedral. So, at each temperature there is a, at each of these phase transformation, although they are not Curie temperature, but because of the there is a ferroelectric the dielectric constant also goes through a peak here, where and that is associated with the crystallographic change, not the Curie temperature. This is the Curie temperature, this is the only Curie temperature, but otherwise wherever there is a crystallographic change you also get some discontinuity in the dielectric parameter or dielectric constant. So, this is one phase transformation, this is another phase transformation and there are in fact 3 phase transformations and 4 polymorphs. You will also notice there are other characteristics. This has been taken from a single crystal, not a polycrystalline material. Polycrystalline we do not get such sharp peaks, they are little blunt peaks and you will also see there are 2 other characteristics. One is there is a tremendous amount of anisotropy, there is tremendous amount of anisotropy so far as the properties are concerned along the crystallographic directions. This is along the A axis and this is along the B axis. Okay. Sorry, this is along the C axis and this is actually along A and B axes. So, A and B axis are same, whereas C axis is different. So, the dielectric constant along the C axis is much smaller compared to the along the A and B axis. Okay. So, this is another one of the more important observation. Other one is there is also some kind of hysteresis here. So, during heating and cooling it follows slightly different path. So, this is your heating and then when cooling it comes follow a slightly lower temperature. So, this is also another characteristic of this phase transformation. This is also called some kind of hysteresis so far as the phase transformations is concerned. It is not a dielectric hysteresis, but a different kind of hysteresis. There is a lag between the heating and cooling directions. So, this is the variation of dielectric constant as a function of temperature and that is associated with polymorphic transformations at different values of temperature. So, this is for the single crystals and the peaks are quite sharp here, whereas if you go to a polycrystalline material, which is the most common material used in industry, these are not so sharp peaks, there are little blunt peaks and you can see the peak is also little blunt and compared to the single crystal form the variation is little not so sharp. Okay. There is another very important aspect also, that is there is a fair amount of dependence on the grain boundary, okay, the grain size particularly in a polycrystalline material. In a polycrystalline material you have different kind of grains, different sizes of grains, and these are actually single crystals put together. So, this grain boundary is some kind of a defect, and that changes the characteristics to some extent. Okay. So, if you have a 50 micron larger size of the grain, dielectric constant is low, whereas higher characteristics are obtained, higher values of dielectric constant obtained when the grain size is small, and that is primarily related to the domain wall movement. Okay. So, domain wall, there is some kind of relationship between the domain walls, size of the domain, size of the domains and the crystals. So, the domain wall movement is restricted. Domain wall movement is restricted when the grain size is very small, and therefore, there is a variation of the dielectric constant as a function of grain size, and one can see 1 micron grain size provides you a very high dielectric constant. So, same material, same composition, but just by changing the grain size one can modulate the dielectric constant, and therefore, one can design different kind of capacitors based on these dielectrics. You can see here the dielectric constant varies from up to 5000 here, and whereas this peak is more than 10,000. Okay. Now, one of the problems, barium titanate is of course used as a dielectrics in many capacitors, various different kind of capacitors, and however, one of the major problems of this ferroelectric ceramics being used in a capacitor is its temperature dependence. Our room temperature is somewhere here around 25 degrees, it may vary up to 40 degrees or so. So, the capacitors are normally used in this temperature range, okay, somewhere here, and you can see from both sides, from this peak as well as from this peak, the tail is coming to that temperature range. So, because of that the temperature stability of this dielectric material is not so good, and the dielectric constant changes with temperature, okay, and that is one of the major problems, because there is a instability so far as the dielectric or the capacitor value is concerned, because of the change in dielectric constant as a function of temperature. So, there is always a attempt to make the dielectric constant as stable as possible by changing the composition as well as the grain structure. And one can see here there is a less step rise or less steep change here in the larger grain size compared to this grain size. This tail of this peak comes very close to the dielectric room temperature. So, one can play with both the composition as well as the grain structure or grain size of the material, so that better and better stable dielectrics can be prepared. Most of the time, in fact, in the industry there are various grades of dielectrics all based on barium titanate ceramics, but many different dopings, many different other dopants are used which goes into solid solution, sometimes forms a grain boundary phase. Is not always a single phase material, but sometimes they are multi-phase materials or dual phase materials, and that actually impedes the motion of the domain wall movement, and therefore modulates or modifies the dielectric property as a function, particularly the temperature dependence of the dielectric property. So, many different compositions are available in the industry with different kind of standards, and they are used for different purposes. The capacitors, some of them require very high dielectric constant, so that the miniaturization is possible, but whenever you have a high dielectric constant, the temperature dependence is also high, the temperature variation is also high, so they are not that stable. However, if you want a very stable dielectric material or stable capacitor value independent of temperature, then you normally the dielectric constant goes down. So, there are many different standards available in the industry, and one has to play with the composition as well as the grain size of the material, so as to generate either a very high dielectric constant material with less of temperature stability, whereas one can also get better temperature stability with relatively low dielectric constant. So, these are some of the industry needs for so far as the dielectric constant is concerned. However, barium titanate is one of the major components of, always been a major component of ceramic dielectrics, primarily because of its very high, relatively high dielectric constant. Normal linear dielectrics will have a dielectric constant of the order of 10, maximum 100, whereas here with barium titanate one can get as high dielectric constant as several thousand, up to 20,000 or to 30,000, right. So, that is one of the great advantages of barium titanate ferroelectrics. Of course, it does not really use the ferroelectric property for this particular purpose, except a very high dielectric constant. So, with this we come to a close of this part of the discussion. We have some more discussion still has to continue on ferroelectric, particularly the different other. We have discussed primarily with barium titanate, but there are many other ferroelectric ceramics which will have similar properties and some applications also. So, that will be continued in the next class. Thank you for your attention.